SwayamPrabha. Digital India. Educated India.
Hi friends, now we will start discussion on the second part of the module, efficiency improvement of power plant. In the first part we have discussed on the power generation flow sheet and its performance, different types of losses and thermodynamic cycles which are used to understand the operations of the power plant and its performance, and cogeneration and heat recovery options for the improvement of the efficiency of the process. In this part we will discuss on overall plant efficiency, energy analysis of steam process, then types of turbines and their cycles for power generation, working of combined cycle and efficiency improvement, and finally efficiency calculation through thermodynamic laws. Here we know that thermal efficiency is equal to energy generation rate into time divided by amount of material used into calorific value of that material into 100. In the first part we have discussed on this. Now we will see how this thermal efficiency is dependent on different parts and how the overall efficiency can be calculated. So, overall plant efficiency, that is dependent on the efficiency of boiler, efficiency of turbine, efficiency of generator and efficiency of works. So, turbine, generator, boiler and works, these four efficiencies will influence the overall efficiency of the unit. For boiler, efficiency T for turbine, efficiency G for generator and efficiency works for works. So, now we will see how the steam process works or a boiler works. In a boiler, our objective is to generate the steam. Objective is to generate steam. So, we have some heat input heat, and we have some output. So, input energy in terms of heat in water, as well as we are also having some heat in the fuel and air. So, this heat is the input to the system and then it is giving us steam. So, some energy is stored here. So, that is our output, energy output. And in between this process we are getting some loss of energy. So, this is the concept of energy, input to output and some losses. Now, how this generation is going on? If we think the steam generation unit, then we can divide it into some parts. Like the first part, the main part is a boiler. We will send here water and through this we will get flue gas after combustion here, say, then flue gas will come out from this boiler unit and it will be having some heating value also. So, here the exhaust of the boiler that will go for heat recovery, that is called economizer. So, economizer Here we will put some water that will be heated and that can be recycled back to this boiler, so that some sort of heat is recovered, and then from boiler we are getting the steam. That steam has to be superheated, so we need superheater. Then superheater will increase the pressure and temperature of the steam that will be used in turbine. So, the whole generation system, steam generation system, we can divide into boiler, economizer and superheater. The three main unit we can consider. In some cases, this water is also preheated, as we have discussed in the first part of this module, that this is optional, in some cases it is used. So, our boiler, superheater and economizer are three main important parts. So, we have shown here that feed and water is coming to economizer, then evaporator, then super. So, this boiler is evaporator. So, these are the parts. Now, we will see how the energy conversion is taking place here. So, what is our input and what is our output, what is our losses, then what is the energy balance in this system. Now, we are going to discuss on that. Now, let us consider some amount of fuel is used in the combustion unit. So, it is releasing its heating values, so high heating value. So, that will give HHV and that will be associated with the flue gas, and flue gas will be used to produce steam. So, if we use 1 kg of, or say if we use WF kg of feed here, if we use WF kg of feed here, feed in this case any fuel, in our case may be waste, and if it produce Ws kg of steam, that means this is Ws kg of steam, then what is the useful energy? What is the useful energy? Useful energy means the energy which is available with the feedstock, part of it is converted to steam, that is useful. In some cases the heat is also used for the production of this steam. We are using some amount of energy here in the economizer, we are using some amount of heat here, some amount of heat in economizer, some amount of heat in boiler or evaporator, and some amount of heat is here also. So, total heat we are using, that is available in our steam. So, that is useful energy. So, useful energy in this case, if we define it as Q1, that is equal to Ws by Wf. Ws is the kg of steam generated and Wf is the kg of fuel we are using. So, Ws by Wf is the steam generated per kg of feedstock. So, this into, so this much of, say if we use 1 gram of or 1 kg of feed, so Ws by Wf of steam will be generated. That means same amount of water was used, same amount of water was used. So, that was the heat of that water, the temperature of that water was raised in the economizer, and then there was some evaporation, then again temperature change. So, if we see here, the H1 is the enthalpy of the water of this Ws by Wf amount of water is, and H1 is the enthalpy here, and H2 is the enthalpy here after evaporation, and then H3 is superheater and H4 is here going to turbine. So, if these are the enthalpy of the water and steams at different stages, then useful energy will be Ws by Wf into how much? H2 minus H1 plus, here one interesting point is that we are producing, this is saturated steam. So, if in our plant you have number of turbines, the one turbine will be at higher pressure. So, higher pressure steam will be exit from the turbine after use and it will be having lower pressure. It may be possible that if the downstream turbine is using lesser pressure, that exit from the first turbine can be used here. The steam exit from the first high pressure turbine can be used here. So, steam from high pressure turbine. So, we are assuming that M1 mass fraction of steam is added in this place. So, we do not need to raise the heating value of the steam from H3 to H4 of that all steam which is generated here. So, we will be in that case 1 minus M1 into Ws by Wf, that amount of heat content will be used, will be increased. That is why this will be 1 minus M1 into H3 H4 minus H3, H4 minus H3. So, this is the heat content in or energy we are getting in useful form, that is in kg per kilojoule per kg of feedstocks. So, that is in kilojoule per kg of feedstock. This is our useful energy. Now, we will consider what are the losses. What are the losses? Then if we get useful energy and if we get loss, then heating value will be heating value which is available with the feedstocks, that is equal to available energy plus losses. So, available energy and we have defined it as useful energy, available energy or useful energy plus losses. Now, what are the losses? Let us see. The first loss we can get here, if moisture is present in the feedstock, if the feedstocks which we are using that is having some moisture or water. So, heat which will be liberated here in the combustion chamber, some amount of heat will be consumed by the water available in the feedstock, and to raise its temperature from the ambient temperature say Ta to T 100 degree centigrade in the boiler 100 degree centigrade for its vaporization, and then 100 degree centigrade to this output, the temperature of gas, exit gas temperature. That is why some amount of heat will be consumed here and some amount of heat will be consumed by the steam to raise its temperature, and some amount of energy will be used to phase change from water to steam. That is why the loss due to moisture content in feed, that is equal to M moisture content into Cp dt for the water. So, Cp is equal to water, Cp water into dt. What is dt? 100 minus Ta. So, 100 minus Ta plus M lambda, that is equal to latent heat, and Cpg steam, Cp of steam into Tg minus 100. So, this will be the heat consumed by the moisture available in the feedstocks, and that will not be used for the steam production here. So, this is our loss. Now, if we put the value of CPW and Cp steam, then this loss is equal to m into, we can get 4.187 into 100 minus Ta plus this lambda is equal to 2256.8 kilojoule per kg, and specific heat of steam, that is equal to 2.09 kilojoule per kg per degree centigrade. So, 0.09. So, that will be Tg minus 100. So, this is our heat loss due to moisture present in the feedstock. So, some other losses, if hydrogen is present in the feedstock, then hydrogen will also be converted to water, and that water will further use some heat that will not be used in the process. So, in this case, loss due to hydrogen content in feedstocks, that is equal to 9 into H into this one Q2. Why so? Because this hydrogen which is available in the feedstock, that will work with the oxygen, then it will give H2O. So, H2 plus half O2, it will give us H2O. So, 2 gram of hydrogen is giving us 18 gram of water. So, 1 gram hydrogen is equivalent to 9 gram of water, and that 1 gram hydrogen will produce 9 gram of water. That is why 9 into H into this Q2, that will be the heat loss due to the presence of hydrogen in the feedstock. We will be having some other losses also, like energy loss due to unburned carbon. So, all carbons present in the feedstocks may not be completely converted. So, some unburned carbon will be available. So, the heat content of the unburned carbon we are not being able to utilize in this case, and that is why it is loss. So, unburned carbon, in ideal cases, the which is in unburned, that can react with oxygen and it can give us CO2. So, in this case del H is equal to say 394 kilojoule per mole. So, this is the heating value of this. So, depending upon the carbon which is not burned, will lose some amount of energy, that is our loss. That is why heat loss due to unburned carbon, we can write that how much carbon is present unburned, that is C minus CAB absorbed, how much carbon is absorbed, total carbon minus C absorbed. So, that is the unburned carbon, that into heating value of this one. So, heating value we have seen here, that is 394 kilojoule per mole. So, 394 divided by 12 kilojoule per gram. So, into 1000, that will be kilojoule per kg. So, that is equal to, we will get 32833 into C minus CAB into kilojoule per kg. So, that is the loss. What is that kg? Kg carbon. This is not the feedstock, this is carbon. Next, other loss we may have energy loss due to dry exhaust gas. So, dry exhaust gas means after this steam generation, the exhaust from the boiler or evaporator, this will be having also some heating value, that is Tg, it is having that Tg. So, it will be having some heating value. So, that if we do not use any other heat recovery unit, so that is going to be lost. So, loss due to dry exhaust gas. So, this is our Q5. So, what is this? We have to see how much exhaust gas is generated. W DEG, dry exhaust gas. So, WDEG is the mass of dry exhaust gas which is generated per kg of fuel. Then WDG into CPDT. So, CP of that gas into DT. What is DT here? That is TG minus TA, TG minus TA. So, this is the TG and originally we had that TA. So, TG minus TA. So, this is the amount of heat loss we are getting due to this reason. Now, we will see loss due to incomplete combustion. So, incomplete combustion means carbon which is present in the feedstocks that can react with oxygen, that can give us CO2, or this can react with oxygen and give us CO, or CO can further be reacted to give CO2. So, here del H is equal to minus 394 kilojoule per kg, here del H is equal to minus 111 kilojoule per kg. So, here del H is equal to minus 283 kilojoule per kg. Now, if the carbon is not completely combusted, this reaction will not proceed and we will lose this amount of energy. So, per kg of carbon we will be losing minus 283 kilojoule of energy. So, loss due to incomplete combustion will be equal to 283 divided by 12. This is per kilomole, sorry, this is per mole, this is per mole and this is also per mole. So, to this into 1000, that is equal to 23583 kilojoule per kg. So, that is due to loss of carbon. Now, we have to convert in terms of kg fuel. So, this conversion can be done if we know the composition of the flue gas. It will be having CO, it will be having CO2, it will be having nitrogen and it will be having O2. O2 will be available because in the previous modules we have discussed that for complete combustions O2 is to fuel ratio should be higher. If it is lesser, then complete combustions may not take place even though stoichiometric oxygen is provided. So, some amount of oxygen may be available. So, in this case if we know the mole fraction of these all those, so mole fraction of CO divided by mole fraction of CO plus mole fraction of CO2 plus mole fraction of N2 plus mole fraction of O2. So, this will be the amount of CO present in amount of total gas, flue gas. So, now if we multiply it with the molecular weight of this in terms of mass, this will be 28 into CO, 28 into CO plus O2, that is 32 into O2 plus 28 into N2 plus 44 into CO2. So, that will be the mass ratio in this. So, out of this much of total flue gas, this much will be the CO. Now C plus O2, that is giving us CO half O2, that is giving us CO. So 12 gram will give us 28 gram of CO. 12 gram of C will give us 28 gram of CO. That is why the loss due to incomplete combustion in terms of kilojoule per fuel will be 23583 into 12 by 28 into this one, 28 CO divided by 28 CO plus 32 O2 plus 28 N2 plus 44 CO2 into this will be. Now this term is becoming is equal to 10107 into then W DEG into 28 CO by 28 CO plus 32 O2 plus 28 N2 plus 44 CO2. So this will be the loss due to the incomplete combustion of this. Next loss is due to convection and radiation. So we have here some furnace, we have some boiler, etc. So furnace, from the wall there will be heat radiation and convection. So if we know the total area, exposed to ambient air, so from this everywhere there will be some radiation and there will be some convection loss. So if we know the total area and if we know the heat transfer coefficient for convection and radiation, then the temperature difference T furnace minus TA for this case, for other cases, if we consider this will be the higher loss because the temperature is not that much here. So maximum loss will be there. So this will be the total loss due to radiation and convection, that is equal to Q7. Next we will see the energy loss due to moisture coming with air supplied. So moisture which is coming here, we are providing air for the combustion, it may contain some amount of water. So that moisture which is available here, that can be determined on the basis of humidity of the air. So humidity of the air, so Q8, that is equal to say humidity of the air into amount of air used, WA, into Cp into Tg minus Ta, that is the temperature change from ambient to Tg. Now in this case the air containing the moisture, the latent heat is not considered. Next is energy loss due to ash and slag. So ash and slag will be generated in the furnace, so that will be having also some amount of energy that will not be used for further applications, and in this case the slag means total carbon minus CaB, the unburned carbon plus ash into Cp into dT. dT means Tf furnace minus Ta into Ta. So this is the amount of heat loss due to ash and slag. So now we have got almost all the losses. So we can get HHV, that is equal to Q1 which we have got, that is useful energy, plus the losses. Losses mean sum of Q2, Q3, Q4, Q5, Q6, Q7 and Q8 and Q9. So this is the HHV equations. So what will be the efficiency in this case? Efficiency will be useful energy, that is Q1 divided by HHV, Q1 divided by HHV. So, that efficiency that is equal to Ws by Wf into, we have got, that is H2 minus H1 plus 1 minus M1 into H4 minus H3 divided by HHV. So, this is the efficiency of this. Now, we are coming to discuss on different types of turbines. Already in the first module we have discussed, first part of this module, the different steam turbine, gas turbine and both combined cycle can be used. So, here this is the working of this. In case of steam turbine, the steam is produced here and it is coming to turbine, and then electricity is generated, and after condensing this is recycled back. Already we have discussed these things. Similarly, the turbine cycles we have also discussed in the first part of this. So, here it is sent, compressed, and then combustion takes place, and then the combusted gas is passed through the turbine, gas turbine, and then we get some work here, and this temperature is around 1500 to 1800 degree centigrade, we have discussed in the first part of this module. And this is your combined cycles, means steam and gas both turbines will be available. So, first the turbine, this turbine will work first, gas turbine, it will work first, the exhaust of the gas turbine will be used for steam generation, and then condensation will be going on. So, this is the combined cycle operation, and in combined cycle, as both type of turbines are used, so loss of energy or loss of heat is reduced. So, efficiency is more. This is the thermodynamic laws which can be used to understand the efficiency. For example, here in this process, if we use EF, the energy of the feed, Ex external energy, and we get product energy EP. So, then the one parameter has been considered, that is NEPR, net energy production rates. For the first law, net energy production rates is considered, that is equal to EP minus NF plus MEX divided by NEF plus MEX. So, this is proposed by this scientist, and normally M is equal to 1 and N is equal to 0, because M is what? Fraction of external energy content diverted to other than sellable product. So, this is equal to normally 1 and N is equal to 0. So, N2 expression is EP minus Ex by Ex. This indicates that the NP is always positive, that means the energy which is produced, that is much more than which is consumed. The second law gives us some another parameter, that is net energy availability, and net energy availability is defined as A is equal to H minus HO minus T into S minus SO. So, H is the enthalpy of stream at flowing condition, and HO is the enthalpy of stream with all components in equilibrium with environment, and similarly the S and SO are, and TO is the temperature of environment. Now, this is similar to del G equal to del H minus T del S. So, gives free energy relationship. So, second law gives us some availability analysis, and it is net energy production ratios can be calculated by second law availability analysis for various types of hardware and chemical reactions to help pinpoint where improvements potentially reside and the magnitude of the improvements, means where we can put more efforts for the improvement of the efficiency. So, up to this on this module, and thank you very much for your patience.